I'll try to shout.
Are you really at your max? Because we really barely hear you.
See if that, is that any better?
It's a little better.
Can you hear us better now?
Not him.
We don't have content for you yet. Is content being sent?
Not at present, it will be shortly.
We've got the greatest minds at work here. Just give us a moment.
It's online, but it says larger images.
Yeah, it's just such a picture.
Yeah. But then it says like,
Hey,
it's definitely larger images. That's the one that I'm on right now. And it has like,
No, it's actually live content coming from my computer.
Somebody's calling.
We're gonna switch to HDMI.
It's in there.
And he's in charge of the ceremony.
It's an interesting name. I wish that was my name.
It's a family name.
Hey man, who knows all my heritage?
Let's take that one out.
Uber, what have we got in here? Oh, yeah, pipeline.
Danny put up like a freaking snake. Go fun one I
Get a good look for that.
My apologies.
So Dan, are you sending content?
Not yet, just give us a moment. They're still getting sorted out.
Now, we're just wondering if it was our projection system that was not working, but.
So you should be getting content now, perhaps?
Oh.
Maybe we need to.
Oh, we can see.
Well. It's not showing on the right screen at our end, but this could be our issue. Is it displaying correctly at McGill or at U of T?
Looks good.
Yeah.
Yeah, that's an us problem.
The board.
So it's the tech guy in.
I don't think the projector is on though.
Yeah, so if, as far as we're concerned, we're sending the content now right now, but if you guys are seeing it on the wrong screen, that's gonna have to be an adjustment on your side.
Can you grab that? So it'll be input so I can see maybe a bigger version.
Yeah, right, and it's.
But I might need to see their screen in case students have questions or they've lost the content or something.
I'm just gonna call back into the system and right now.
Okay,
I can keep toggling through if you prefer.
no, that was good.
Stay with that one. Yeah, sorry. 1 second.
So they just dropped. They're gonna call back.
That's good. So if you guys can just bring it up on your own computer, because you're gonna have a hard time seeing.
Yeah, and if you want to, if you start the slideshow here.
Yeah.
You are in.
But we've lost this.
Now, is that the input button right there?
Yes, I believe so. Daniel, that's the one you did for content share?
Content share.
It's this one right there.
Yep. Oh, actually, this is switching, I believe. So you know, this is switching camera.
I see. So you can go from camera and content.
Yeah,
Okay.
they can see.
Yeah.
Okay, let's see.
Does that make sense? So if you want to switch between, that's what we're all right here.
Okay, so let's get the content up there because they want that. Okay. Now, if I want to toggle the streams, How do I toggle the screen? Yeah,
And that's actually the one.
okay,
So that little single controller.
okay. Can I see?
That's awesome. Yeah.
Why can't that mouse cursor, why is not that coming up on that?
So sliding mode, the presentation mode,
You want to see this?
I mean, I can sort of see.
Yeah,
Okay. So we.
well, I don't want this, I want to have that.
okay, then we need to go,
We need to get a percentage on here. Presentation.
Which one?
Slideshow.
show.
You don't want presenter mode?
No. I want to be able to, yeah, so they can see the mouse there now.
Yeah.
Hopefully.
Yeah.
Laurent, are you with us? Hello?
Hi, Dan. Yes, we are with you, but we cannot hear you too well, and I'm trying to get your display on our big screen, and it's not working at our end.
Okay.
The best we can do is just.
So are you as close as you can to your microphone?
Now.
Is that any better?
Yeah.
Is that any better?
It's more clear.
Hello?
Well, I think it will have to do, but it's pretty. It's not very loud. Let's just say.
Okay.
We're gonna do a quick toggle here to see if that changed anything.
And what we'll do is we can start right now, Dan, and we do see your display on a very small portion of our screen right now, but everyone's got the lecture notes. So we'll start by following your lecture notes and recording the lecture anyways, and hopefully our IT tech will come in and help us out at some point in the next couple of minutes.
Perfect. Yeah, if you have control of a Polycom unit or whatnot on your side, there should be an adjustment on how to display that content. If you are seeing something, that means we are sending you the feed, and unfortunately that's the best we can do from our side. Any adjustments otherwise need to come from you guys over there. Did that come through okay?
Okay, go ahead, Dan, whenever you want.
Okay, but can you hear me? That's the main thing.
Okay,
Yeah.
during the main presentation. One request we might
Just
make.
be as loud as possible.
Can we request a mute on the far side participants unless you guys are having a conversation? That will help the system clarify the audio, because I believe on both sides we're using a speakerphone, and speakerphones work the best when the people that don't need to be heard are muted until they are needed to be heard. Does that make sense? Okay, I'm gonna assume the far side got muted there. We don't have any indication that they're muted. Usually, yeah, she's muted. Yeah, we see it there.
Okay.
The other location.
All right, let's get this going.
Sure. Just so you understand that otherwise you're competing with their room volume. If their volume is louder, they're gonna overwhelm.
Okay. Something's going on though, because previously we didn't have this audio issue, even when their speakerphone was on.
Yeah.
All right. Sorry about that.
No, sorry about that. We will work on that after this.
Thanks, Maddie. Hopefully this will go smoothly. All right, let's get going here. I'm going to talk to you today about some applications of geochronology as applied to structural geology with a focus on shear zones. What I'm going to talk about can be broadly applied to most situations where you're trying to constrain the timing of deformation. But for sure, when it comes to shear zones, knowing that timing as accurately and precisely as possible is extremely important. I'm going to focus mainly on the higher grade ductile shear zones, mainly because the chronometers that we use, as far as providing what are called absolute ages, based on generally on isotopic analyses, those minerals that we use are generally grow as metamorphic recrystallization products during the deformation. It's much harder at lower metamorphic grade or at below any sort of metamorphic recrystallization temperatures to absolutely constrain the timing of deformation, although I'll get into that in one of the case studies in the next lecture next week. And so what it boils down to when you're trying to figure out the structural history, in general, the geologic history of an area, one of the questions that you should be asking yourself is, you've been told to do geochronology or that it's important, but you should be asking why. Why do you do it? Because it's time consuming, very time consuming. It takes a lot of effort to collect the samples correctly, to prepare the samples. It's very costly most times, especially if you're using another lab rather than your own. It takes a lot of effort just collecting the samples, but also doing the analyses and making sense of the analyses. And many times, you can ask my students and Laurent's students, it doesn't always yield satisfying results. You come up with very complicated systems in which the results you get are very difficult to make sense of. And so you end up hitting yourself and getting all upset with the results, but in general, you should be trying your very best to try and get these age constraints. And so why do we bother knowing all these things? Because putting age constraints on deformation and on orogenic processes is critical. So in order to understand what's going on, you need to put it in a time context. That's absolutely critical. And so age constraints for deformation for shear zones, that tells us when that deformation happened, when it stopped, perhaps how long that deformation lasted for, the rates of deformation, and sometimes if you have seemingly different or the same styles of deformation, did they occur at the same time or did they occur at different times in different parts of the map area or the region you're working in? So these age constraints can also provide critical insight into orogenic processes, such as the duration of orogenesis in general, the rates of crustal thickening and exhumation, the rates at which a given shear zone that's particularly important to you, what that rate of shear, of deformation was with respect to that shear zone. So there's many, many things that can fall out from getting reasonable age constraints for the deformation. And I'm going to try and summarize for you how we go about getting those age constraints, what techniques are available to us, which ones are more appropriate for a given situation than others. There's lots available to us now, and so part of the problem is actually figuring out what's most appropriate for the problem you're trying to solve. So in general, we start out by making observations at various scales. You might be identifying initially a shear zone or a particular geologic structure that's important to your research, looking at maps, air photos, geophysical analyses of the region, aeromag, gravity, and you begin to target in on a particular structure, or in this case a shear zone, and you definitely want to go and take a closer look at that, no doubt. And so you go to that next level of observation, perhaps at the outcrop scale, and you begin to make those observations at the outcrop scale to constrain the geologic relationships that allows you to better understand the character of that shear zone. Whether it's brittle, whether it's ductile, what style of shearing was it? Was it simple shear? Was it pure shear or some combination, general non-coaxial shear? These are the observations and the data you would be collecting at those different scales, whether it's map scale or outcrop scale. And then typically you begin to take samples that you can take back to the lab, and you take a closer look at them. And the closer we look at these things, sometimes the more information that falls out of it. And therefore, the age constraints that you are trying to determine should also be based on the scale of observation, the scale of the information that you're trying to correlate these age constraints with. Because many times, especially in the past, the question was, you've got ages, but what are they truly constraining? Are they constraining the timing of the deformation, or is it something else? And you may be getting misleading age constraints, and we'll look at that in a moment. But what I would say is you want to get age constraints down to the level of observation that you're getting your information from, that you're using to characterize the geologic relationships of the shear zone, of the geologic structure you're working on. And so here's an image of a thin section, and we can see here, this is a big staurolite porphyroblast. Within the staurolite, there is a inclusion trail here that perhaps you can assign to be an earlier phase or generation of deformation. That's discordant with the external foliation here. There's a penetrative transposition foliation. In this case, it was termed S2, perhaps the second generation of deformation that was observable at this scale. And then that's overprinted by these crenulation folds and crenulation cleavage S3 here. And using this scale of observation, we can get quite a bit of information about the hierarchy of deformation and its relationship, in this case, to metamorphic recrystallization. There is an earlier metamorphism that grew staurolite that captured these inclusions, and this earlier formed inclusion trail, and then that was overprinted by a later generation of staurolite growth that is inclusion poor. And so what you would want to try to do is provide age constraints that you can correlate with the best information that you have at the scale that information was acquired at. And very typically that comes down to looking at the microscopic scale. And so some natural questions that you should be asking yourself when you're trying to provide some age constraints and do the analyses that will lead to age constraints is, when did a given generation of deformation occur? That's first and foremost. And secondly, what is the relationship between the deformation and the metamorphic recrystallization that may or may not have accompanied that deformation? We know that there's an intimate coupling between the deformation processes that are involved in the development of a shear zone, the higher grade shear zones that is, and metamorphic recrystallization. It's sometimes I refer to it as a mutually catalyzing relationship, in that the metamorphism is a key process in facilitating ductile deformation. As Laurent has talked about in past lectures, the metamorphic recrystallization is part of that recovery or annealing process that allows the deformation to continue to move dislocations through a crystal lattice, through things like dislocation creep and volume diffusion. And the deformation in turn helps to facilitate metamorphic reactions by weakening atomic bonds, helping to redistribute material, also providing added strain energy to the system, which in turn can push through critical energy barriers that lead to metamorphic recrystallization. But when we want to really understand these relationships between the deformation processes that resulted in the deformation products, the strain products we see within a shear zone or other structural features, and that relationship to metamorphic recrystallization, to understand that, you really, truly need to have age constraints. You need timing constraints. Without it, you're basing some of your information on speculation, on the preserved relationships that may or may not truly reflect that relationship you're trying to establish between, say, metamorphic recrystallization and deformation. And so for the rest of the lecture, I'm going to focus on looking at how we go about establishing, first of all, the geologic relationships, sampling strategies, the techniques that are available to us, and how we should go about choosing what is most appropriate for the problems that we're trying to solve, because that can be a significant factor in whether or not the ages you acquire are meaningful or not with respect to the structures that you're trying to provide age constraints for. And so it's very important to understand how those age constraints were produced. Whenever you see them, if you read them in journals, if someone's telling you about them at a conference, you should have the critical part of your mind asking, how were those age constraints produced? What techniques were used? What geologic relationships were established that these age constraints are being correlated with? Because that will ultimately answer whether or not those ages are meaningful. And I can tell you there's a lot of ages that are published that are not meaningful. And so when you want to understand if they're meaningful or not, it boils down to the following fundamentals. One, the geologic relationships, so critical. This is where the field work, the time spent looking at the rocks, establishing those relationships, doing petrography, doing everything that you can to provide as much information as possible that allows you to best characterize those geologic relationships. Without that, those ages are meaningless. Two, you should be asking what chronometric system was used. And we'll see a number of them that are available, but not all of them are appropriate for particular problems, whether you're dealing with higher temperature deformation or lower temperature deformation. There are certain chronometric systems that are better suited for higher temperature versus lower temperature age constraints. And three, which techniques were used. We'll see that. I'm going to talk in a second about this relationship between precision and accuracy, and the technique that you use can be very important as to whether or not you're achieving the precision that's necessary to allow you to differentiate perhaps different generations of deformation and when they happen, and accuracy, which is ultimately what we want, because you want to have the most accurate ages that reflect the actual timing of those events, of those deformation events that you're trying to constrain the ages for. And so this is a cartoon by Gary Larson, but it was augmented somewhat by a fellow named Mike Villeneuve, who was a geochronologist at the Geological Survey of Canada, and he was getting quite fed up with geologists coming in, trying to get some ages, and Mike would provide these ages, and then they would just go run roughshod with those ages and do whatever they felt was best for the model that they were trying to put forward. And so you can see here the geochronologist is saying, well, that's a lousy age, 1,024 plus or minus 1,000. That's absolutely meaningless. Make sure you don't use that. But what he jokingly says the geologist here is that blah, 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 1024, blah, blah, use that. And I put that in there because it's not as bad today, but back in the day when we were getting age constraints, especially isotopic age constraints, there were many times when it was quite doubtful that they were truly constraining the age of the deformation in this case, and they would go ahead and publish these ages. And once they're published, it's like it's the word of God. You've published it, it's there, and forevermore you have to have faith that it's correct. But in reality, it is quite misleading, and until someone goes along and reanalyzes those rocks, those ages become part of the permanent history for that particular geologic problem that was being addressed. And so when you're dealing with age constraints and trying to provide timing of deformation of shear zones, you should always be keeping in mind this relationship between what is precise and what is accurate. And there's an analogy you can use. I'm sure many of you have seen this before, where you can use the analogy of a dartboard or a target that you've been shooting at. And if you have a spray of your bullets in this case, it's not very accurate and not very precise. You can see in the top left image here. And then as you move over to the right, you have a more of a even distribution about that bullseye. And so you can see that that's accurate, but it's still not very precise because of that distribution is not tight around that bullseye. And then in the lower left here, we see that the bullet holes are now quite tightly grouped together, but they're all grouped away from the bullseye. So this is an example of where you could have age constraints that are very precise, and I'll talk about certain techniques that provide very precise age constraints, but they're not accurate in that they're not providing meaningful timing constraints for the particular geologic feature, shear zone in this case, that you may be wanting to provide timing for. And so ideally what you want is you want as best as possible analyses that are very tightly grouped together, statistically are very reproducible, and they're accurate. They are reflecting, based on all of the information that you've gathered, meaningful timing constraints for that geologic structure that you're trying to better understand. Unfortunately, it's not always possible to have both precision and accuracy, and sometimes you have to compromise, and perhaps for the sake of accuracy, compromise your precision somewhat. And I'll get into that in a moment when I'm talking about the different techniques available to us. So there's many chronometric systems or techniques available, and different types of minerals that we can use for providing age constraints for geologic structures and shear zones. Some of them include uranium, thorium, and lead, and that's one that has been a very popular in the last greater than 50 years now. And there are certain minerals that are very common in rocks, especially zircon and monazite, that have enough uranium and a daughter product lead in them that allows us to get fairly precise ages for the rocks that those minerals grew within. There's other chronometric systems such as argon-argon or potassium-argon before we started using argon-argon. And those include the micaceous minerals, muscovite and biotite, also hornblende here, and K-spar, common minerals that you can date with argon-argon. That's typically a lower to moderate temperature chronometer. Lutetium hafnium and samarium neodymium for garnet. These are becoming back in vogue, becoming more popular for dating those higher temperature rocks and higher temperature shear zones. The zircon and apatite fission track, that would be a lower temperature chronometer. That's where you're getting 150 degrees Celsius down to about 50 degrees Celsius. Same thing with the zircon and apatite, uranium, thorium, helium. And then there's rubidium, strontium that used to be quite popular, but now it's becoming used less and less, and mainly because it's a whole rock analysis. And so you can imagine that you're mixing together what could be quite complex isotopic systems that have either been altered or reset through time. But nevertheless, it's still available to us. I don't have time to go through all of these different chronometric systems. In fact, there's many other ones that are available. There's also cosmogenic dating, there's helium dating, there's, of course, radiocarbon dating. But I don't have time to go through those or even fully treat any one of these systems thoroughly in the time that I have. But if you are interested, or if you're looking at some other system that I don't cover today, for sure there's some textbooks out there that you can start with, like Bauer and Mensing or Dicken textbook. And I also provide a fairly detailed bibliography at the end of the lecture within the PDF that you can take a look at. Just keep in mind that, you know, there's more and more up-to-date references that could be added to that, but you can certainly begin with that bibliography that I provide for you. Okay, so I'm going to focus mainly now on the uranium thorium, but mainly uranium lead, and this will be something you'll look at in the lab as well, labs 1 and 2. But if you have questions about these other isotopic systems, please feel free to ask me about it. You can send me emails or you can ask me during the lecture here. But for the time being, I'm going to focus on one of the main systems, the uranium lead and sometimes thorium lead systems that are often used when it comes to constraining absolute ages for geologic structures. I should have mentioned at this point that there are two primary ways of providing age constraints for structures. One is referred to as relative age constraints, and that's based on the geologic relationships. You see that there's a shear zone, and then it's been exhumed and eroded and has an unconformity atop of it. And so the shear zone must be younger than that unconformity, and the shear zone also must be older than any rocks that are incorporated into the shear zone. So those are relative timing constraints. An example of that. The absolute timing constraints, these are where you actually provide analyses, typically isotopic analyses that lead to a quantifiable, repeatable age analysis that can be applied to the deformation, to the structure, the shear zone, what have you, and those have an error associated with it, and so those are referred to as absolute age constraints, and that's what I'll focus on here is the absolute age constraints, in particular using uranium and lead. Okay, so when dealing with the uranium-lead system, which is one that I'm most familiar with, there's many techniques and unfortunately a lot of acronyms that are associated with those techniques that are available. And I've put up here about 5 of the most commonly used techniques, but it's not all of them. So the first one here, IDTIMS, that refers to isotope, dilution, thermal ionization, mass spectrometry. And that essentially, you're taking a crystal like zircon, you're chemically dissolving it, usually in hydrofluoric acid. You're separating out the uranium and lead, and then you're isotopically analyzing the isotopes of uranium and lead using a mass spectrometer. And this was the standby for decades, the IDTIMS. And it's highly precise, but we'll see in a bit that, especially when I talk about the case studies, it's not always very accurate because of the fact that you're dissolving a whole mineral rather than doing in situ analyses, such as using ion microprobes, such as a SIMS, a secondary ion mass spectrometer, or a SHRIMP, which refers to sensitive high resolution mass spectrometers. These were a huge advent in the 80s and 90s when they first came on scene. This changed geochronology significantly in that you could take minerals such as zircon or monazite or titanite or a thin section, and using a beam of a primary, called a primary beam of usually oxygen, you could sample in situ very small spots, that monazite or that zircon within the rock, and so you could preserve the textural and fabric information and try to correlate the age you get from these, either of those two ion probe techniques with the deformation that you're trying to constrain. So this was a huge leap forward in providing more accurate and meaningful ages. The problem is they're less precise than the ID-TIMs. And then not too long after the SHRIMP and SIMS became available, people started using lasers with the inductively coupled mass spectrometers. So this now is known as an LA ICP-MS, laser ablation, inductively coupled mass spectrometry. And very similar to the ion probes, you can do in situ analyses, and instead of a primary oxygen beam, you use a laser. Literally, you use a laser. And the laser ablates a little spot from your zircon or monazite, and you analyze the isotopes that are ionized from that spot using a mass spectrometer, and you eventually can produce ages that are correlatable with, again, with textural and fabric information that's preserved for that particular sample. Another one, electron microprobes. This became quite popular in the 90s because many universities, many earth science departments have electron microprobes available. They're a lot cheaper than, say, a ID-TIM system or an ion probe. They're actually much more expensive now than laser ablation systems. But because many metamorphic petrologists and other geophysicists and geochemists use electron microprobes, there are many of them available. And this became quite popular, but there are many drawbacks to it in that you can't do isotopic analysis. You can only do elemental analyses, and so many assumptions have to go into the use of electron microprobes and the ages that come from it, and so they're becoming less and less popular these days. And then there's fission track analyses. These are the lower temperature type of geochronometric analyses. They look at the actual damage in a crystal caused by fission of, say, uranium within a zircon or apatite. These analyses are quite extensively used when looking at low temperature deformation in the 150 degrees and lower type of deformation, and exhumation of those rocks, say, within a shear zone. I'm not going to get into that too much because that, again, is a whole other series of lectures that require a lot of time to do it justice. So I'm going to focus mainly on the uranium-lead side of things, looking at techniques such as ID-TIMs, ion probe, laser ablation, but how we can use these in combination to provide the best possible answer for the problem you're trying to address with respect to getting age constraints for structures. So before I start, I'm just going to go over some geochronology fundamentals first. I assume most people are quite savvy with these terms, what's an isotope, what's an atomic number and whatnot, but I'll go over it just so we're all on the same page, and then we'll move forward looking at the techniques in more detail. And so what's an isotope? Well, we all know that atoms have protons and neutrons within the nucleus, and then there's a electrons that are in a cloud around that nucleus. And the number of protons within an atom, of course, determines what atomic number or what element that atom actually is. And it's the variation in the number of neutrons within that nucleus that creates an isotope for any given element. So a certain element like uranium always has 92 protons, but it will have a differing number of neutrons within its nucleus that produces the isotopes of uranium. The ones that we're most interested in as geochronologists are uranium-238 with 146 neutrons versus uranium-235 that only has 143 neutrons. And what's really valuable about isotopes of a given element like uranium is that those isotopes are unstable and they will spontaneously decay for uranium in this particular instance to produce daughter isotopes of lead. And they're different isotopes, these daughter isotopes. And so we can differentiate which lead isotope was the decay product of uranium-238 versus which lead isotope was the decay product of uranium-235. During that decay, and it's not one particular decay event, there's a whole series of them that we won't really get into too much, but the decay products of, say, the decay of uranium-238 or uranium-235 could include alpha decay, which that involves the ejection of what's called an alpha particle. That's why it's called alpha decay, which is essentially helium that has the 2 neutrons, 2 protons. And also it involves the ejection of a gamma particle and an electron. Beta decay, or sorry, not electron, energy. Beta decay, that involves the neutron ejecting an electron and a proton and some energy, and there is the emission due to beta decay of an electron. So you're basically changing a neutron into a proton at that point. And the last one is the electron capture. This is where an electron is brought into the atom, and that changes a proton into a neutron plus some energy. This involves the electron being drawn into the nucleus and combines with a proton to make a neutron. So these different types of decay are all involved in the radiogenic decay or fissioning of isotopes like uranium-238 and uranium-235. So, of course, there's a lot of energy that is produced during the decay, the spontaneous decay, and that's why nuclear energy is so popular, because it doesn't take very much in any concentration of these, say, uranium isotopes to produce a lot of energy. I'm going to look at a little more detail about the uranium and thorium geochemistry of certain minerals, in particular actinides, that are the popular minerals for using in the higher temperature uranium-lead age analyses. So both uranium and lead, or uranium and thorium, are incompatible elements, and they're taken up in greater concentration in many of the actinide-bearing minerals, and therefore they tend to be enriched in the crust and in silica-rich rocks compared to other more mafic rocks such as basalt or anything that's derived from the depleted mantle. Because these elements, uranium and thorium, are incompatible, they're readily taken up initially in partial melts that then eventually crystallize these minerals such as zircon and monazite. At a smaller scale, they're enriched in later phase minerals and accessory minerals. The uranium and thorium are enriched in these minerals because as the melt is crystallizing, they're so incompatible that the initial crystallization products are not really taking in these uranium or thorium. And it's really the last gasp of the crystallization of that melt that leads to the incorporation of uranium and thorium. And so some of the common minerals that we find that are enriched in uranium and thorium are uraninite, thoriumite, zircon, thorite, alunite, monazite, apatite, xenotime, sphene. But I'll focus mainly on zircon and monazite because those are two very ubiquitous minerals in many different rock types, and they tend to have quite a bit of uranium and or thorium incorporated into their crystal structure. Uranium and thorium are also present in minerals because due to their incompatibility and their ionic radius or their size, there's certain minerals such as zircon and monazite where these elements of uranium and thorium are more easily incorporated into the crystal structure because they can be substituted for other similarly sized elements with a similar valency, such as zirconium 4+, which has an ionic radius of 0.87 angstroms. And so it's easily replaced by uranium and thorium. And the same thing goes for in monazite, where you have the replacement of some of the other rare earth elements that tend to be incorporated into monazite that have a similar ionic radius to uranium and thorium. And so that's why zircon and monazite and these other minerals tend to be enriched in uranium and thorium because of their some of the elements within them have a similar ionic radius and valence to zircon and uranium and thorium. So as I mentioned before, the decay, the fissioning of uranium and thorium doesn't happen all in one event. There's a chain of decay, or it's referred to as a decay series. And so uranium and thorium, their isotopes are each the parent of a chain of radioactive daughters that end with a stable isotope. For uranium and thorium, they end with a stable isotope, one of the stable isotopes of lead. And each of the decay chains for uranium isotopes, 238, 235, and thorium isotopes, say 232, thorium, they always lead to the formation of a specific isotope of lead. So it's not random, it's very specific, and that's why we can measure with certainty a certain isotope of lead and know how much of the parent isotope of uranium or thorium must have decayed to produce the final amount of the stable lead isotope for that parent uranium or thorium isotope. And we can see here in this chart on the right, this is the, you might not be able to see it very well, but this is the decay series for 238 uranium. And you can see there's quite a few what are called intermediate decay products or intermediate decay daughters of uranium-238 that eventually, through time, lead to the accumulation of its stable lead product, 206 lead, the isotope of 206 lead. And so we need to be mindful of this fact that there are these intermediate decay products for uranium because that can have some influence on the isotopic systematics and your overall 206 lead that you measure at the end, say for 238 uranium. And I'll touch upon that a little bit later in the lecture, but we need to be aware that there are quite a few intermediate decay products for these uranium and thorium isotopes. And I should mention too that thankfully for the purposes of geochronology, the intermediate daughter products of uranium and thorium, their rate of decay is quite fast compared to the overall rate of decay of the initial 238 uranium. So 238 uranium, for instance, has a very, very long decay rate on the order of many billions of years. And the intermediate daughter products here have decay rates typically on the order of milliseconds to sometimes up to 10,000 years. But overall, it can be considered what's referred to as secular equilibrium, in that the amount of time that we're looking at typically in millions of years, when you're talking about geologic history, we can assume that the rate of decay of the parent is matching the accumulation of the daughter product, because those intermediate daughter products are decaying so fast that by the time the next parent product decays, the intermediate daughter products have all decayed down to the stable isotope of lead. And so what we measure today, as far as the lead is concerned, we can assume matches the number of parent isotopes that have decayed through time to produce that lead. And that's referred to as secular equilibrium. And that's a major assumption that goes into the age equation that we'll be looking at in a moment. And so some of the main isotopes of uranium and thorium that are used are 238 uranium. That's one of the main ones. It's quite abundant, and it decays eventually to 206 lead. There's 235 uranium here, and that decays to 207 lead. There's 232 thorium, which is quite abundant in minerals such as monazite, and that decays to 208 lead. So this is an absolute that you can always depend on, that 238 uranium will always decay to 206 lead. 235 uranium always decays to 207 lead, and 232 thorium always decays to 208 lead. The next thing that we need to understand is that there is a very reproducible rate of decay that's been measured over many decades for each of these parent isotopes that decay to their daughter isotopes, their stable daughter lead isotopes. And so for the decay rate for 238 uranium is about 1.55125 times, oh, that should be 10 to the minus 10 here, not A. And that equates to a half-life of about 4.47 billion years, which is great when you're trying to constrain ages of geologic features, especially on Earth, given that the Earth is about 4.55 billion years old. This means that this is a very appropriate half-life for dating geologic structures that are in excess typically of 1 million to 10 million years old. 235 uranium has a much faster decay rate. We can see here 9.8485 times 10 to the negative 10 per year. And that equates to a half-life of about 704 million years. So it's still quite a long half-life, and it's still quite appropriate to use for constraining geologic ages for features, especially on the Earth. 232 thorium, it's got a much longer decay rate here. It's 4.9475 times 10 to the negative 11, which equates to about 14 billion year half-life. Again, it's still fairly appropriate for any geologic features that are reasonably old, older than 1 or 10 million years old. And we'll see in a moment this relationship between 238 uranium and 235 uranium, those two parent isotopes, we can pair those together and use them as a check against each other. And so uranium-lead system has been extremely popular for many decades, and it still is, because you have this dual chronometer with one elemental system, the uranium-lead system. Today, the ratio of 238 uranium to 235 uranium is around 137.88, and this is a fairly constant. Anything that you measure today, you could take a strand of hair, you could take a blade of grass and you could measure that uranium isotopic ratio, and it should come out to about 137.88. So as I mentioned before, one of the major fundamental assumptions that go into the age equation that we'll look at in a moment is this concept of secular equilibrium, in that uranium or thorium bearing systems that have remained undisturbed for a few million years, they reach this state of secular equilibrium where there's established between the abundances of successive parents and daughter nuclides in the uranium and thorium decay chain, such that the decay rate, or you could call it the activity of each daughter nuclide in the chain, is equal to that of the parent. Basically what that boils down to is that because the intermediate daughters in that decay series for a given uranium or thorium isotope, because those intermediate daughter products decay so quickly compared to the parent, what we measure at the end after, say, a time span of a few million years or more, we can assume that the daughter product that we measure equals the number of parent isotopes that decay to produce those daughter products. That there's no significant amount of intermediate daughter products that would represent a significant amount of decay of the parent product that's not reflected in the measured stable lead isotope at the end. And so we can treat the initial parent decay as being reflected by the concentration that we measure at the end for the stable lead daughter products. And so whatever we measure, say in 206 lead, we can treat that as reflecting the total amount of 238 uranium that's decayed. And same thing goes for 207 lead, for 235 uranium, and 208 lead for 232 uranium, or thorium. So that's a very important assumption to make. And that only holds if you're looking at systems that are on the order of a few million years or more. Because once you start looking at very young structures or any geologic feature that's very young, say less than 1 million years old, then that accumulation of intermediate daughters does become significant with respect to the overall stable lead isotope concentration that you measure today. And that needs to be taken into consideration. And actually, it's fortunate that that's the case, because now that allows us to date very young features. We can use those intermediate daughter products and their decay rates as a technique for analyzing and providing age constraints for very young features. I won't get into that, but certainly that's something you can keep in mind if you're dealing with very young geologic features. Okay, so assuming secular equilibrium has been attained, that allows us to formulate the basic equation for radioactive decay. And let me see if I can get my pen up here. Oops. And so we see here in this first equation, we have P. That's the parent isotope, and it leads to, or that's the parent isotope that we measure today. And that is equal to what was the initial concentration of the parent isotope multiplied by the exponential of the negative decay rate for that parent isotope times time. And so as long as, in theory, as long as we can measure that initial parent isotope, as long as we can measure that final amount of the parent isotope, and we know its radioactive decay rate, and we know the time, we can calculate what the original amount of the parent was. Or vice versa, if we can get that end amount, the present day amount of the parent isotope, and we can somehow figure out what the initial amount of the parent isotope was, and we know its decay rate, which is a constant, we can get the amount of time that must have transpired to change the initial parent to the final parent concentration. Where am I here? Okay. We can also say that if we consider the daughter here, sorry, I can't see the little pointer. There it is. So if we consider here, let's take into consideration now measuring that daughter stable isotope. And so this is the present day daughter that we could analyze. Perhaps it's 206 lead, which is the stable lead isotope for the fission of 238 uranium. We can use that in turn to calculate what the amount of the parent, original parent isotope was versus the present day amount that we can measure on the mass spectrometer. And so we take that daughter isotope and we can say that the amount of the daughter isotope is equal to the original amount of the parent, and we substitute this equation in for the parent isotope that we measure today. And what we're left with is that the daughter is equal to the original parent times 1 minus the exponential of the negative decay rate times time. And eventually what we can say is that reorganizing this equation based on what we have up above here, we can substitute this part of the equation here for the parent isotope that we measure today. And so we can say that the daughter isotope we measure today is equal to the parent isotope we measure today multiplied by this part of the equation here, which includes the decay constant and time. And so now we're getting down to a point where as long as we can measure the daughter isotope and we can measure the parent isotope today, and we know the decay constant for that parent isotope, we can eventually figure out the amount of time that must have transpired to produce that daughter isotope. And so reconfiguring this equation, we can say that the daughter isotope is equal to the amount of the parent isotope measured today multiplied by the exponential of the decay rate times time minus 1. Reorganizing this equation, this is what we want. The time that's expired since the crystallization of the zircon or monazite or whatever radiogenic mineral you're looking at is equal to 1 over the decay constant for that parent isotope, say 238 uranium, multiplied by the natural log of the measured ratio of the daughter and parent isotope plus 1. That's the age equation when it comes to uranium lead, thorium lead, argon, any isotopic radiogenic system that you are trying to use for age analyses. This is the age equation, and this is what you're trying to find here, is that time t that has transpired since the crystallization or the event that you're trying to provide age constraints for. So let's take a closer look at the uranium-lead chronometers that are available. And as I said before, having these two chronometers available, sorry, it's really hard to see. These two chronometers, the 238 that goes to 206 lead and 235 that goes to 207 lead, this is extremely useful to us as geochronologists, as geologists who are trying to get age constraints, because it serves as a check against each other, these dual chronometers for the uranium-lead isotopic system. That's because the decay of the naturally occurring isotopes of 238 uranium and 235 uranium gives rise to two independent chronometers that we can calculate this time t here using the age equation for each of those two independent chronometers, 238 uranium to 206 lead and 235 uranium to 207 lead. You can then use those two equations to calculate compatible sets of 206 lead, 238 uranium, and 207 lead, 235 uranium. And those each give specific values of time. And we'll see why that's so important, because if they give the same time, same absolute time, you know that you're getting the proper accurate age for that particular crystal, say of zircon or monazite. And so the beauty of that system is that any uranium-bearing mineral, such as zircon, monazite, titanite, there's a whole slew of them available to us, will contain both of those chronometers, which can be used as a check against each other. That has been extremely useful to us when it comes to high temperature deformation and trying to constrain the ages of shear zones or other geologic features that are usually assigned to the higher temperature end of the spectrum. Why don't we take a break here, and we'll come back in about 5 or so minutes, and we'll move on with the rest of the lecture.
The end of the song is that tone, and so like I'm just sitting here, and every time I turn on like pink.
It worked fine. Why they
I wasn't trying to take naps in my butt. Just like,
that's pretty simple.
I remember it's like, no.
Then when it does call.
Yeah. The problem is like I know all this stuff.
Yeah, that's it.
This is just review.
Then it should.
It's fine. It's fine. It's review. Oh yeah, I remember that equation now. I remember that. It's good that we have a source that I can go to just quickly and be like, there's all this stuff.
It's all stuff that like you look at it and you're like, I should remember this.
And then the site will
Yeah,
call
I
itself in.
remember it just because I did it last year.
Okay, yeah.
Like I remember it like straight up because we did it in Ron's course.
Yeah.
course. So like, and that was one of my favorite courses. So like, I remember all of it.
No, I did this in like metamorphic metrology and then again in like global tectonics, but that was like, you know, sometime of like winter of 2013. So it's been some time.
Yo, you want to see the model setting?
I tried it.
You want to see? See the models? Oh yeah.
We're at the mercy of technology, and when technology fails.
Everything just fails.
Well, they shouldn't have fixed what wasn't broken first.
When do these usually get posted? Like, will this get posted?
The recorded thing?
Yeah, no, yeah. Is that a Christie thing?
It's Christy that does that, but usually she.
Are you guys ready at your end, Laurent?
Hello? Yep.
Are you all ready, or do you need a few more minutes?
Maybe give a couple of minutes. Some people have stepped out to use the facilities.
Okay. Laurent, would it be helpful if I say, change to next slide, or are you able to at least see that?
No, we do see your slide whenever you're changing it. It's just very, very small. But luckily, everyone's got your PowerPoint on their own computer, and so we're seeing the slides as they change.
The colors.
Okay.
Thanks. We're good to go now.
All right. Okay, so continuing on with the Geochron fundamentals here, and we can see here on this next slide that there is the age equation. I'm just gonna, and this is what we want to always be mindful of when we are using, say, uranium-lead, and we get those two independent chronometers. What we want to check once we apply that age equation for each of those chronometers, the 206 to lead to 238 uranium and 207 lead to 235 uranium, is whether or not the dates or the ages that are produced are the same. And that's referred to as being concordant. And it's only concordant as long as the following conditions are satisfied. The first condition is that the mineral has remained closed. It's very important to uranium, thorium, and lead, and all the intermediate daughter products throughout its history. So this is a big assumption that goes into the providing of age constraints, is that you're assuming a closed system. If it hasn't been closed, then there are problems that need to be addressed, because the ages that you will acquire will not be concordant, and they will not provide meaningful ages unless you can figure out what went wrong as far as not being a closed system and how you might mitigate that with your analyses. The other one, the next assumption that needs to be met, is that the correct values are used for the initial lead isotope ratios such that the lead that you measure today, you're assuming either the zircon or monazite or whatever mineral you use did not incorporate any initial lead. It's also referred to as common lead. If it did incorporate common lead, then you have to subtract that from the lead isotopic measurements you make today. That's vitally important, because otherwise you can imagine if you have a certain amount of unaccounted for initial lead, that's going to raise your apparent concentration of the lead isotopes you measure today, which will exaggerate or inflate the ages that you calculate based on what you measure today. The third is that the decay constants are known precisely and accurately. And for uranium-238, uranium-235, and thorium-232, we know those decay constants very accurately. They've been measured for many decades now, and we know them to 4 or 5 decimal places. Nevertheless, there is still an error that's associated with those decay constants that's quite often overlooked in the assignment of error for the absolute ages. And so that's something you should be keeping in mind, is have the decay constant errors been properly accounted for the isotopic system that you're using, because some of the decay constants are not nearly as precise and accurate as the uranium and thorium ones are. For instance, the argon decay constant, potassium to argon, has in recent times been adjusted, and if people are using the old decay constant, you may be getting misleading age information, as an example. Fourth is all the analytical results are accurate and free of systematic errors. And this comes down really to the quality of the lab and the machines that you're using to make your isotopic measurements. If the lab is rigorous, they are keeping very close track of any systematic errors, either present time systematic errors that may be due to electrical issues or static issues, or day-to-day, week-to-week, or long-time running systematic errors. And those need to be very, very precisely accounted for when analyzing your uranium and lead isotopic information, and taking those systematic errors into account when you're propagating the errors through for your age analysis. And that comes down to having confidence in the lab that you're using. So you need to do your homework. The lab that you're going to use, you want to check and see that they've been rigorous in accounting for these systematic errors. When you have your uranium and lead data at hand and you begin to calculate the ages that you are going to try to assign to, say, the age of your shear zone or the age of some other geologic structure, one of the common ways for plotting that uranium-lead data is to plot it within what's called a Weatherall Concordia diagram. That's a very common one, where we have on the y-axis 206 lead, 238 uranium. And on the x-axis, we plot the ratio of 207 lead to its parent product 235 uranium. And in this Weatherall Concordia diagram, we see here that there is a curve. And that curve is referred to as the Concordia curve. It's curved because of that differential decay rate between 238 uranium, which has a half-life of about 4.4 billion years, and 235 uranium, which has a half-life of about 704 million years. And because uranium-235 is so much faster in its decay rate than uranium-238, early on in Earth's history, the initial accumulation of 207 lead due to the decay of 235 uranium versus the accumulation of 206 lead due to the decay of 238 uranium, that initial accumulation of 207 lead was very rapid relative to the 206 lead accumulation. And therefore, you can see that this part of the older part of the Concordia curve from about 4.55 to say around 2,500 million years ago, that part of the decay curve is fairly flat in its trajectory. And that's because we're accumulating very quickly 207 lead versus 235 uranium versus 206 lead over 238 uranium. But there's an inflection point around 2500 where that decay, the Concordia curve, begins to get quite steep as we approach present day at 0 million years ago, present day here. And that's because at this point, the amount of 238 uranium left versus the amount of 235 uranium becomes quite elevated in 238 uranium. So even though 238 uranium is decaying much slower, the overall accumulation of the daughter products is heavily favored towards 206 lead. And presently, there's about 138.88 238 uranium atoms versus every 235 uranium atom presently. So you can imagine that the accumulation of 206 lead now far outweighs the accumulation of 207 lead as we approach present day. We use this Concordia diagram very commonly to plot our two uranium-lead chronometers, the 206-238 and the 207-235 chronometers. If the ages that you get for those two independent chronometers are the same, it's referred to as a concordant age, and the analysis should plot right on the Concordia curve. And so those analyses that plot on the Concordia curve are referred to as concordant analyses or concordant ages. Ideally, this is what we're trying to acquire in our age analyses. As if we get concordant ages, most times we're quite happy that we are getting meaningful ages. If it doesn't plot on the Concordia curve, those analyses are referred to as discordant analyses. And in particular, if they plot below the Concordia curve, they're referred to as normally discordant. And the reason why that is, it seems a little counterintuitive that if it's below, it's referred to as normally discordant, versus if it's above, it's referred to as reversely discordant. The reason why we call those below normally discordant is that most discordant analyses will plot below the Concordia curve because usually you're combining some part of that isotopic system that is older with some part of that chronometer that's reflecting a younger event. And the combination of those two events together would result in analyses plotting somewhere below the Concordia curve on a line that connects the older and younger events. The upper event would be referred to as the upper intercept. We'll come back to this in a moment and look at it in the lab. And the younger event would be the lower, oh, that's terrible printing, but the lower intercept. The cause of the normal discordance, which is actually very common in your analyses, I guarantee you will almost always get some normally discordant data, can be due to a number of complicating factors that breach those fundamental assumptions, the closed system assumption in particular, that goes into calculating the ages based on your analyses. One is that you may have an issue with lead loss, that one or both of the stable lead daughters has been lost, the system has been open, and those isotopes of lead have leaked out of the system. Another possibility is that you have inherited older grains. So maybe you have a zircon, and very typically minerals like zircon, like monazite, not so much, but definitely zircon, they tend to have an older seed around which the younger, either magmatic or metamorphic zircon has grown around. And so it's not uncommon, especially for zircon, to have an inherited older core to it around which you have a younger age of metamorphic or igneous crystallization. The third primary cause of discordant data is that you have some younger overgrowth, either a metamorphic recrystallization event or an igneous event. Maybe the rocks have been partially melted and you've overgrown that initial zircon or monazite or whatever radiogenic mineral you're looking at, you've overgrown it at some younger time due to either a metamorphic event overprinting it or a second igneous event like partial melting affecting those rocks. Ideally, if you have measurements of your uranium-lead system that leads to normally discordant data, if you're lucky, it would be a two-component system, one that involves one component of an older age and one component of a younger age. And if it is only a two-component system, then what you can do is you can regress or draw a best fit line through those data that connects the older event with the younger event, and it will be a perfectly straight line referred to as a Discordia line that is best fit through these analyses that are normally discordant. And typically there are computer programs that do this for you. You don't have to do it by hand anymore, thank God. And if you're lucky, you have a two-component system, you get a very nice straight Discordia line. The analyses all fall on it within statistically reasonable overlap of the errors of those analyses. And you can have confidence that you're constraining an older event at the upper intercept and a younger event at the lower intercept. And so actually, these sorts of data can be quite instructive in that they give you additional information. You can get more than just one, say, younger age constraint here. You can actually begin to constrain some older event as well. Unfortunately, many times, what will happen is you're going to get a shotgun pattern of normally discordant data. And you can drive through or regress through a number of best fit lines, and it becomes anyone's guess which one of those best fit lines most accurately represents whose upper and lower intercepts most accurately represents the timing of the structures of the geologic features that you're trying to constrain. And so when you have data that's in more of this shotgun pattern, that's a very good indication that you should be looking at other techniques to try and better limit the inaccuracy of the ages that are being calculated, because there's something that you're not accounting for. Maybe you're mixing older and younger domains. Maybe there's been multiple lead loss events. Something's happened that's creating this shotgun pattern, and it's unlikely you're going to be able to extract meaningful information from it. And so that's when you should be considering looking at other techniques that may limit the imprecision of the accuracy that you're getting in this technique that provided the shotgun of pattern of data. And we'll look at some of those techniques in a moment that you can consider using as alternatives. Another chronometer that's quite popular as far as thorium-bearing minerals such as monazite is this chronometer that's the 232 thorium parent isotope that goes to 208 lead. I'm not going to get into it in too much detail here, but there's a mineral monazite that's thorium rich. And unfortunately, because monazite's thorium rich, it tends to take in one of its daughter products in a significant amount. Or sorry, it takes in thorium in a significant amount, and the main isotope of thorium that it takes in is 232 thorium. But zircon, which takes in a lot of uranium, one of the intermediate daughter products in the 238 uranium decay series is 230 thorium. And it hangs around long enough. It's got a decay rate in the tens of thousands of years, and it hangs around long enough that as the zircon is crystallizing, it will take in quite a bit of 230 thorium. And so young zircon will have what's called an excess of 206 lead, because part of that 206 lead budget is coming from this 230 thorium that was incorporated from the bulk rock and not from the decay of 238 uranium that was taken initially in by the zircon. And so that's just a word of warning with respect to the uranium-lead system, is that sometimes all is not as wonderful as you might think with the uranium-lead system, in that there are these issues of the intermediate daughter products for the 238 uranium system. And so sometimes it's worth considering, using another isotopic system such as the thorium-lead system that will mitigate this problem of unsupported or excess 206 lead in the 238 uranium system. I only bring this up as an example that when you are choosing your isotopic systems, your geochronometers, keep in mind some of the issues. Do your homework, try to figure out, are there any issues that might give me misleading ages, and how might I mitigate those issues? So for example, instead of using zircon, maybe I'll use monazite, because I can use that thorium-lead system that's not affected by this intermediate daughter product problem where 230 thorium leads to unsupported accumulation of 206 lead. And so I provide for you here a list of different minerals: zircon, monazite, zinitime, rutile, apatite, thorite, titanite. There's more and more minerals that are at our disposal today. You can do uranium-lead analyses on K feldspar even, because the techniques that we have available to us are becoming higher and higher precision, meaning that we need a lesser and lesser amount of a concentration of uranium and lead in a particular mineral to be able to repeatedly produce the uranium-lead ratio that we use in that age equation. And so the moral of this story is, don't get hooked on one particular mineral or one particular isotopic system for providing your age constraints, because you've become accustomed to using that. You're comfortable with it. Sometimes you need to stray away from what you're comfortable with and go with what you know would be a more meaningful system or a more meaningful technique. In this next image here, I provide a table that shows us the different minerals that are available, say for uranium, lead, the amount of uranium that is typically incorporated into those minerals, enough such that they can be analyzed and used as for uranium, lead, age constraints. The amount of common lead, which is important to consider, that's taken in by these minerals when they first crystallize. You can see here, for instance, that zircon takes in very, very small amounts, almost vanishing little amounts of common lead, versus, say, titanite, which takes in quite a bit of common lead and can be difficult to mitigate when you're doing your analyses and trying to calculate your final age from those analyses. In this last column here, I provide the rock type that you typically find these minerals in, these uranium and lead bearing minerals. You can see here, for instance, why zircon itself is so popular, because it's found in almost all rock types. Ultramafic rocks, not so much, but most other rock types, there's a chance, good chance that you're going to find zircon. Some of the other minerals here, bedelite, that's very good for ultramafic rocks as an example. So this column here provides for you a way to assess, given the rock type, given the geologic structure that you're trying to date and what types of rocks that you have at hand, there are certain minerals, certain geochronometric systems that are more appropriate than others. And so that's something you want to assess as you're strategizing about the type of technique, the type of mineral that you may be looking at using for the problem you're trying to address. You know, you want to consider the rock type, the age of the structure. Is it Precambrian? Is it Mesozoic? Or is it Holocene in age? And the temperature at which the deformation occurred at is also very important in choosing which one of these chronometers you might use in your analyses. So something else that you should be considering when you're thinking about what technique to use, what mineral to use, you know, you could list what are the strengths and perceived weaknesses of those techniques, of the minerals. And what I will suggest to you is that you not constrain yourself to a particular mineral or a particular technique, that you keep your mind open and you combine techniques, if need be, that combine the strengths that will provide for you the best possible answer. Don't pigeonhole yourself based on someone's biased against one technique or another. I can tell you firsthand that many geochronologists and geochronology labs, they are, for obvious reasons, very convinced that their technique is the best and that other techniques in other labs are not as good and that you shouldn't even consider it. But my advice would be, consider all of the options available to you and go with what provides for you the best possible strategy for providing meaningful age constraints. So here I provide some examples. Start out looking at IDTIMS, the isotope dilution thermal ionization mass spectrometry. So this is where you take a mineral like zircon, you dissolve it in strong hydrofluoric acid, you separate out the elements of uranium and lead, You measure their isotopes on a mass spectrometer, and it's extremely precise, ID-TIMS. It's the most precise technique for isotopic age constraints. Typically, you have errors in the order of less than 0.1. Even now, they're getting down to less than 0.01% of the age that you're dealing with. So you can analyze very young rocks, even rocks, volcanic rocks, for instance, that are less than 1 million years old, very precisely, almost to a weekend. Well, not quite, but some might claim that. I list here the perceived, underlined, perceived weaknesses for it. Some of them are real weaknesses and others are perceived because the strengths will outweigh the weakness. One definite weakness of the ID-TIMS technique is that you basically lose the sample. Your zircon, your monazite, what have you, you've dissolved it, it's gone forevermore. Once you analyze those isotopes, there's no going back and repeating those analyses. You can take another zircon from the same rock and do the analyses, but you can't take that particular zircon that was initially analyzed. It's gone. And therefore, because you have to dissolve that zircon or other mineral like monazite, you have to remove it from the rock by crushing and grinding techniques and doing gravity separation and magnetic separation. And therefore you lose the textural information, which can be crucial for correlating those ages with the deformation, with the metamorphic recrystallization. Another perceived weakness is it's very time consuming and very expensive, typically on the order of $2,000 to $3,000 per sample. So make sure you're convinced that's the best technique for you before you invest all that time and money into it. Another technique for uranium lead is the SHRIMP, the sensitive high resolution ion microprobe. And this is great in that as far as spatial precision is concerned, it is excellent. You can do what are called in situ analyses. You can take a thin section where you've identified the location of zircon or monazite or titanite, and you can put a shrimp spot on it, the primary oxygen beam, which typically is around 20 microns. You can adjust that to bigger or smaller diameter. And so you can put analytical spots on that zircon or monazite in situ. So it's very spatially precise, 5 to 30 micron spatial precision. It's essentially non-destructive. 1 to 10 nanograms of sample is lost due to the ablating by the primary beam. It's relatively quick, so you can go in there in one day and analyze a few samples, where ID-TIMS it's going to take months. And you can analyze relatively young rocks, perhaps as young as tertiary in age, because of the precision of the shrimp. A perceived weakness for the shrimp would be that it's not as precise as TIMS. So if you want to get it down to plus or minus 10,000 years, you'd probably use the TIMS technique, but you're going to lose that spatial precision and you're going to lose that textural information, which could be the most important part of your timing constraints. The shrimp is also very expensive, $3,000 to $4,000 a day. And in Canada, in particular, there's a lack of access to the shrimp. We only have one in Canada, and so you have to plan at least a half a year in advance, if not more, and you have to write a proposal to demonstrate that the analyses you're going to undertake are useful and meaningful. Laser ablation, this is becoming more and more popular, mainly because it's the amount that it costs to set up a laser ablation ICP-MS is significantly less than an ID-TIMS lab or a shrimp lab. The strengths that are it's reasonably precise, the errors are on the order of 1 to 2% of the age. It's very quick and relatively cheap, down to about $8 per spot. Usually you do about 100 spots though, so you're looking at least on order of $1,000 per sample. It's excellent for what are called detrital zircon work, where you're trying to constrain the age of deposition for sedimentary rocks. I won't get into that, but it's really good for that. And you can analyze relatively young rocks, typically that are Mesozoic and older. It's a little problematic as you get younger than Mesozoic in age, but you can still do it. Some of the perceived weaknesses, it's not as precise as the TIMS and shrimp, so your errors are going to be bigger. The spatial precision, at one point, this is actually a bit outdated now, at one point the spatial precision was not as good as the shrimp, but now there are labs where their spatial precision is, in my opinion, as good as the shrimp. So this is no longer a perceived weakness, in my opinion. Another weakness, I would say, is that most labs are only capable, when it comes to uranium lead, of analyzing zircon. And that's because you need what are called standards. You have a really well-characterized standard of zircon that you know the age of very precisely, and you can put that standard in, you do your unknowns, your own zircon, and you go to that standard and you check to make sure that the age of that standard matches its known age. And typically, zircon, there's lots of great zircon standards out there, but when it comes to monazite and other minerals, there's not as good and well-characterized standards available. So typically, laser ablation labs lack good standards. Electron microprobe, I'm not going to get into this right now. It was very popular at one point. It's becoming less and less popular as more laser ablation systems are becoming available. But one thing about the electron microprobe that has the best spatial precision, you can actually analyze domains within a zircon or monazite that are less than a micron in width. And so extremely good spatial precision. It's very quick and cheap. You can usually do analyses on a sample for under $500. And the nice thing about the electron microprobe is that you can do some other things with it. You can analyze and map for trace and major elements, which can be very useful when correlating those ages of the zircon or monazite with other minerals or other geologic structures that you think you can correlate these major and trace element ratios with. The weakness is not as precise. It requires a ton of lead, so it's only appropriate to use the electron microprobe in rocks that are older than or Precambrian in age, not Mesozoic. And it's a little bit of a black box because at one point so many labs were trying their hand at it. Everybody had their sort of own analytical protocols, and there wasn't no protocols that were agreed upon amongst the labs that were doing it. It's a bit better today, but it's still, you have to be careful. Certain labs are not using as rigorous of protocols as other labs. And so I come back to this image here of comparing precision and accuracy, and how you should be keeping this in mind when you're trying to decide which analytical technique is best. And so I would say it depends on the problem you're trying to solve. If it's precision, absolute precision in the age, you're trying to get it down to plus or minus 100,000 years, then do ID-TIMS. But if you're talking about spatial precision and maintaining or preserving the textural information and correlating it with that textural information, then you should be considering in situ techniques like shrimp or laser ablation. Don't pigeonhole yourself to one technique. Keep your mind open to a combination of techniques that together could provide the best possible answer. Very commonly, for instance, I use both laser ablation and ID-TIMS together. I use the laser ablation as a reconnaissance tool, and then I go to ID-TIMS to really nail down a particular age that I'm interested in. Be logical, use common sense. Consider the problem you're trying to solve, and then choose those techniques or multiple techniques whose strengths will provide the best possible answer. And always keep in mind that difference between what is precise and what is accurate. And that ultimately you're trying to get the best balance between the two, between precision and accuracy, to provide the most meaningful age information. And so here I show these techniques, and I put plus or minus symbols between them just to show you that you could use them all in combination, or two in combination, or just one by itself, but ultimately what you want to arrive at is the best possible solution for the problem you're working on. So always consider what's available to you and what will provide the best possible answer. So now some of the nuts and bolts as far as acquiring age constraints. We've gone through the fundamentals, but how really do you go about getting those age constraints? So I'm going to walk you through from the sample collection right through to the data reduction that you'll be doing in your lab. So part of this I'm going to cover in the tutorial for the lab once we get down to data reduction. But for the time being, I'll start out with how, from the very first stage of considering I need to get timing constraints, how do you go about doing that? So first of all, you need to get the information that characterizes the geologic relationships as best as possible. Without those, the ages are useless. You need to be very diligent about getting those geologic relationships nailed down. And you need to be cognizant that those relationships, information can be gathered at many different scales, from the map to the outcrop to the thin section, right down to the atomic scale sometimes, using things like SEMs. And so here I show an example. Here's a map in the northern Selkirk Mountains. We're going to focus in on this red triangle here, which is sitting right on what's called the axis of the Selkirk fan. And I'm just going to walk you through an example of how you go from documenting the geologic relationships to collecting the sample to getting the data and analyzing that data and reducing it to get a meaningful age. And so here's an example of where you have a penetratively deformed schist within a shear zone. There's a late cross-cutting granitic dike here that includes a xenolith of that foliated schist. So we know that this dike postdates the development of this shear zone fabric. Here's another dike here that we can see is infolded with and has an axial plane parallel to that penetrative shear zone fabric. So this dike and some of the stringers coming off of it, depending on their orientation, this dike, we assume, was caught up in the deformation that was part of the development of the shear zone. And then you take a thin section, and I've showed you this thin section before, and you look at the microstructural information in there and see if you cannot better characterize the relationships between the different deformation events that may have affected the shear zone either before or after the development of that shear zone. Once you've very thoroughly documented, as best you can, in the field at least, the geologic relationships, then you move on to sample collection. At the same time, you're still carefully documenting the geologic relationships, but in this case, at the location where you're collecting that sample from. So you want to make sure that you characterize any of the structural information that's available to you, whether it's folds or shear zone fabrics, shear bands. You take lots of photos, make drawings in your notebook, make sure you document exactly where that sample is coming from, so if someone wants to, they can go back and resample it or check your relationships. And then you want to collect as much sample as reasonably possible. If you're in a truck, take a bucket full. If you're walking with Sherpas, you know, load up those Sherpas like Laurent does. Or if you're by yourself and you just have a backpack, you may only want to take a hand sample, but you want to take as much as possible. Also keep in mind that certain rock types will tend to have more of a given mineral than others. Say more felsic rocks will have more zircon in it than more mafic rocks. And so that's another consideration, is that the amount of sample you take is partly dependent upon the rock type. If you know you're dealing with a rock type that's going to be lacking or limited in the amount of whatever mineral it is you want to analyze, like zircon, you're going to have to take more of it. And so just keep that in mind as well. You could go back to that chart that I provided with the rock types and what minerals tend to grow with those different rock types. The next thing you should do, and this is something you should probably work out ahead of time anyway, is which chronometric system are you going to be focusing on? Are you looking at a high temperature shear zone, and so you want to look at minerals like zircon or monazite that tend to be considered higher temperature, minerals that crystallize at higher metamorphic or igneous temperatures? Or are you looking at some lower temperature shear zone that you need to choose minerals like micas, biotite muscovite, or K-feldspar, or using apatite fission tract, something that will provide for you age constraints that are better appropriate or more appropriate for lower temperatures. You may also be limited by the rock type you're going to sample, so make sure you understand where you're going to and what rock types are available and whether or not you can expect to find the mineral that you want to use for the chronometric system that you've chosen. And then you choose whichever chronometric system you think, or systems, multiple, that you think might be most appropriate for providing the best possible age constraint for the shear zone or whatever structural feature you might be interested in dating. You should also be very carefully choosing which technique you're going to use. Sometimes you can get that sorted out well ahead of time, and it's good to contact that lab as far ahead of time as possible to ensure that you're not going to have an issue of not being able to book time when it's needed. And this is very important if you're doing a master's or a PhD and time is of the essence. Keep that in mind, because some labs you need to book that, you know, many months in advance. But sometimes you won't know exactly which technique is the best suited for your problem until you actually collect samples and know that you have a certain mineral available to you. So sometimes that can't always be done, but if possible, try to get that sorted out ahead of time. The next thing you would do is the sample processing. For some techniques like IDTIMS, you're going to take your sample and you're going to crush it and mill it, do gravity separation, magnetic separation, and that's what's considered to be a conventional method for separating out those minerals like zircon and monazite that you might want to isotopically analyze. Otherwise, you may be looking at getting a thin section of that sample because you want to get age constraints at the same scale that you're making your observations at when characterizing the structural information that you're trying to provide age constraints for. And this is an example of a scanned thin section that we had scanned for monazite. This M, all these M's stand for monazite. So all of these little blue dots, if you can see them, represent locations of monazite. And so we would go in here and we would look at each of these locations and think about, okay, which locations are best suited for the problems we're trying to address? Are we trying to address the timing of, say, the porphyroblast recrystallization of staurolite? So maybe we're going to take an inclusion of monazite. Or are we looking at dating shear bands and we want to find a monazite that's sitting within a shear band? And hopefully part of that monazite grew during the development of that shear band. So these are Very powerful techniques, these in situ techniques, the shrimp and laser ablation, where you can take this textural information from the thin section and you've found as best you can all the locations of, say, zircon or monazite or whatever radiogenic mineral you're interested in dating, and then you go in and you target those minerals that will, at least spatially, provide for you the best possible age constraints that you can correlate with the problem that you're trying to address at that time. Up here in the upper right, this is referred to as an epoxy grain mount, and you can see here, this is another way you could separate out those zircon or monazite and mount them in an epoxy grain mount. The problem is you lose all the textural information. The advantage is you can put hundreds and hundreds of zircon or monazite in there, and so you can get lots of analyses, but you lose that textural information. And some other things to consider if you're doing, say, in situ analyses or say something like ID-TIMS, is it's becoming very common now to image those minerals that you're going to eventually analyze either using in situ techniques or ID-TIMS, so you can characterize the internal structure and zoning of those minerals. We can see here in these monazite from this thin section here, some of the monazite have more than one chemical domain in them, and that is indicative of more than one growth event for that particular monazite. Down below, we see some cathodoluminescence images of zircon, and again, these images are very instructive because we now know that there's an inherited core within the zircon surrounded by these beautiful, what are called oscillatory zones that are indicative of magmatic growth of zircon. And so for this zircon, which is from a pluton, we know that there's an older inherited core surrounded by the igneous growth of zircon, but if we were to dissolve that all together, it could be quite problematic in that you mix those two ages together. And so having that information ahead of time can help you eliminate possible techniques to use. Like in this case, I would not use ID-TIMS to analyze that zircon because I know I'd be mixing ages, and if those detrital cores are of different ages, you're going to get that shotgun pattern of data that you can make no sense of. Laurent, should I stop here and then pick up at the tutorial?
Yeah.
Or I could.
Well, you're doing the tutorial today as well, right?
Yeah, it won't take very long. Basically, I'm just going to finish this lecture and then just talk about how the students should handle the data that's available in the lab.
Okay. You guys want to just keep going, or you want a 5-minute break? It's up to you.
We could take a
Take
5-minute break and then.
Let's take 5 minutes so that we can have our minds and brains all fresh up and ready for the tutorial information.
Roger. Anyway, we better get it back down.
Yeah, you can do your thing.
Are you all ready to finish this off?
Right, essentially this.
Yep. All right. Is everybody ready at Queens, back from the bathroom and whatnot? Great, great, great. Okay. So picking up where I left off, so now you're at a point where you're ready to analyze. You've either crushed and ground and separated out your minerals, and you've done your homework and made an epoxy mount and imaged them, or you've got them in thin section and you're going to analyze them in situ. This is where, in my opinion, the fun begins. This is where you start to get good, hard data. Although making sense of that hard data, we'll see in a moment, can be very frustrating. And so you now spend many hours of worried hand-wringing, hoping that your work is all for naught, and you get meaningful analyses. If you've done your due diligence ahead of this point, you have minimized the probability that you're going to get spurious or analyses that are misleading. So if you've done all of your work ahead of this time and been careful about it, you've maximized your probability of getting meaningful analyses. That is what you want, absolutely. If they're not meaningful, you've wasted all your time and money. And so typically what you'll end up with, whether it's working in a lab that your supervisor has, or you go to another lab, you'll end up with a whole mess of initially raw data that's coming right off say the mass spectrometer or whatever machine you're using. And then that raw data has to be reduced. And that means that you get rid of outliers, that obviously there was some issue when that particular analysis was being acquired. Maybe there was a voltage fluctuation. Perhaps you missed the mineral with your spot analysis somehow, or you drilled through the mineral with your spot analysis and you hit the glass or the epoxy. Something went wrong. And so you filter out any of the obviously outlying data, and then you begin to take that huge mass of raw data and you reduce it down to a point where you're left with the most meaningful analyses that can then be used to calculate the ages using that age equation when you're talking about isotopic ages, using the age equation. And so ideally, for uranium and lead and thorium and lead, you try to get it down to reducing that data so you're left with the ratios of the daughter product, in this case the daughter lead product, versus the parent isotope that fission to create those daughter lead products. And you'll notice here this little superscript C here. If I had scrolled down in this table, you would see that there's a footnote for C in that it describes how the common lead, the incorporated lead during crystallization of that mineral, was removed, and this represents only the radiogenically derived lead from the fissioning of the parent product. Okay, and you're going to do that in part one of the lab, where you're going to take or remove the initial lead such that you're left with only the radiogenic lead product. Because if you do not do that, your age will be, will be too high. It'll be exaggerated by the excess amount of the radiogenic lead that has the initial lead counted with it. So you need to remove that initial lead. You will also see here, I should mention, the errors that are associated with these ratios. These are the analytical errors. most commonly reported. Each lab will have a method for calculating and propagating through the analytical errors that are associated with the isotopic analyses of the machine you're using. And you want to know, as a user, make sure you know how those errors are propagated. What's the source of those errors and how they're propagated through? I've been at thesis defenses and I've asked students in the past, how were those errors calculated? What were the sources of those errors? And they did not know this. That is a big problem, because you might be reporting errors that are totally meaningless with respect to your analyses. So make sure you know, ask the person who you're working with in that lab how those errors are propagated, how they're calculated and assigned to the ratios and ages that you eventually calculate. So eventually what you come back with is you've done all this work, you've gone into the field, you've documented these geologic relationships as carefully as you can. You've tried to make sense of them as carefully as you can. You've been careful in choosing your technique, which chronometer, whether it's uranium-lead, argon-argon, fission track, uranium, thorium, helium, carbon dating, whichever chronometer you happen to choose that's most appropriate for the problem you're solving, whether it's high temperature deformation or low temperature deformation, whether it's really old Precambrian or really young tertiary. Then you've collected the sample, you've either separated out or analyzed in situ the mineral that has that isotopic system for the chronometer you're using. In this case, in this example, it's uranium-lead, and I used ID-TIMS. And if you're lucky enough, those data will provide for you meaningful ages. And so in this particular example, I was very lucky. It was during my PhD, and it was one of the first sets of dikes that I collected and analyzed, and I thought I was off to the races, because I could see here that this cross-cutting dike here provided an age of about 156 million years old. So I knew the deformation, that shear zone, was developed prior to the intrusion of this cross-cutting dike. And then I had a deformed dike folded and sheared within the shear zone that gave an age that seemed to make sense of 167 million years old. So I could say that that dike was older than 156 million years old and younger than or equal to 167 million years old. So that's great. I was able to constrain those ages, but sometimes you're left with information that provides for you initially this dreaded shotgun pattern of information. In this Concordia plot, we see here these letters A, B, C, D, and there was many more, and I just didn't have the heart to put it in there because it was too painful of a memory for me. But I spent months acquiring that data, and to realize that those data were not providing for me meaningful information as far as constraining the age of something as simple as a pluton. This is a granodioritic pluton. I had very good control of the geologic relationships between the development of structures and the intrusion of this pluton, and I thought as long as I could constrain the age of the pluton, I could constrain the age of these structures that the pluton cross-cut. Unfortunately, I didn't do my homework ahead of time, and I learned my lesson the hard way. I just took the zircon, I separated them from the pluton, I analyzed them by ID-TIMS, where you dissolve the whole zircon, and when I realized I had this horrible distribution of data, the shotgun pattern, I then went back and I did my imaging, and I realized that there were these clearly old inherited cores of zircon in there that were surrounded by what I wanted to date the igneous generation of zircon that is represented by these beautiful oscillatory zones of the zircon. And so I then went to the shrimp and I analyzed those, the inherited cores, and it turns out they're the detrital zircon ages for the sedimentary rocks, the Windermere supergroup that the intrusion came up into, and incorporated some of these old zircon of varying ages. That was the problem. Some of them were Archean, some of them were Proterozoic. And so a combination of dissolving these old Proterozoic and Archean zircon with some, varying proportion of the magmatic part of the zircon gave me this shotgun pattern of data. And so once I realized I had this problem of these inherited cores, I went to the shrimp, I analyzed those magmatic rims, those oscillatory rims, and I realized that the actual age of the Pluton very consistently was 167 million years old. So the moral of the story is, if I had done my homework ahead of time and imaged these zircon ahead of time, I could have saved myself all of that grief, time, effort, and money of getting this meaningless data. And I could have went right to the shrimp, saved myself all of that time, money, and effort, and got the most meaningful ages for that Pluton. The error on that is about plus or minus 3. For the ID TIMS, you could expect that to be about plus or minus 0.03. So I was getting very precise ages for the ID TIMS, but very imprecise as far as the accuracy is concerned. And so this is where you could give up a bit of the precision in the hopes of getting the most accurate age for that feature. And then the next thing that you can do eventually, hopefully, is that you can, through establishing that time context, you can then make a much better and reasonable interpretation of the geologic history of whatever area, region that you're working in. Once you get that time context, things begin to fall and come together in a much more meaningful and logical way, rather than guessing at what the time context may be. Something else I didn't get into, but you may hear being tossed around, especially when it comes to isotopic analyses, is this concept of closure temperature. This is especially important for minerals that don't necessarily act as a closed system when you raise the temperature in that system. Certain minerals like micas and hornblende that we analyze using potassium and argon, if you raise the temperature enough in that system, they no longer act as a closed system. They become leaky. The argon begins to leak out or leak in. And therefore, you need to be cognizant of this concept called closure temperature. It was something first described, or at least quantified, by this fellow Dodson in 1973. And this is because they began to realize at that time, when they're doing different analyses, that certain minerals were not acting as closed systems. There was information that was indicating that they were opened up at some point in the geologic past. And so the closure temperature, this is in reference to a given mineral's temperature at which little or no daughter product is retained above that temperature. And so once the temperature drops below the mineral's closure temperature, given as Tc, then that mineral becomes a closed system. And you can, by analogy, think of that as the start of its radiometric clock for that mineral. Once the temperature of the system drops below the closure temperature, the mineral has now become a closed system to that radiogenic daughter product, such as lead or argon, in the mineral that you're analyzing. and I'm not expecting you to memorize Dodson's equation, but I would say you should be aware of this term closure temperature, and that certain minerals do have a closure temperature that's geologically reasonable. What I mean by that is certain minerals like zircon and monazite, their closure temperature is well above 1,000 degrees Celsius. There's very few geologic environments in which you're going to crank the temperatures above 1,000 degrees. So zircon and monazite, the concept of closure temperature is not really terribly appropriate. But for other minerals such as the biotite, muscovite, K-feldspar, hornblende, they do have a geologically reasonable closure temperature that's in the range between, say, 550 degrees and 250 degrees, depending on which one of those minerals you're looking at. And that can be very useful in that you could analyze those zircon, and you could say, okay, that zircon crystallized at 900 degrees Celsius, around the attainment of the maximum temperature those rocks were at. And then you have argon-argon analyses from, say, some micas like biotite or muscovite, or both, or hornblende, and you can say that at a later point in time, these minerals cooled enough that those minerals became close to argon diffusion. And knowing the closure temperature of those minerals, you can begin to constrain the rate of cooling and possibly the rate at which these rocks were exhuming or getting higher and higher in the Earth's crust relative to the surface. And I'll show you an example here in a moment. But I should mention that the closure temperature in this equation, the most important things is that there is a, that equation where you're calculating closure temperature here, the cooling rate and the effective diffusion radius are two of the most important factors that you need to try and constrain if you're going to apply this closure temperature equation. And so if you can get a handle on this, this is probably going to be one of the hardest factors to try and constrain in the closure temperature equation, is that cooling rate, the change in temperature over change in time. Sometimes you just have to guess at it, and that means that you're basically guessing at what the closure temperature is. And so that's not a very satisfying result, but you have to start somewhere. And so based on this concept of closure temperature, you can begin to put together a time temperature path for a given terrain that you might be working in. If you use a suite of different minerals whose closure temperatures represent perhaps higher temperature ranges versus lower temperature ranges. Just a minute.
How's it going, guys?
Yeah.
We got a meeting at 1 o'clock?
Oh, okay. We'll be out of here in a minute. Okay, thank you. I'm going to have to leave it off there. The lab is pretty much self-explanatory as far as how you take that data, import it into an Excel spreadsheet, and use Isoplot if you have that available. If you don't have Isoplot available, I do provide the Concordia diagrams that you can hand or manually plot that data within. At the start of next week's lecture, if you have any questions, you can either ask me then or you can send me emails regarding the lab. But it's a fairly straightforward, self-directed lab. And I'll talk to you next week.
Okay, thanks, Dan.
Thank you.
Thanks.
Thank you, Dan.
Bye. Bye-bye.
I wonder why they didn't schedule.